So, hi everyone, thanks for coming. I am Melina, I'm a PhD student in Brazil, and here I'm presenting part of my PhD project, which is still ongoing, so any feedback is very welcome. So here we are trying to understand and disentangle this major axis of variation, of variability in tree vita rates in global forests. So how do I go? Okay. So first I have to thank to my supervisors. I have a nice team of supervisors, also from different institutions, and also the principal investigators of many forest geo plots, this great network. So, oops, I'm going backwards and, okay, forward. So this study is based on the importance of understanding forest demography through the lens of tree vita rates, which is represented here by growth, mortality, and recruitment. So we know that different mechanisms may change the vita rate, so they are influencing and interacting in different ways, the vita rates. And we know many studies that are focused on some specific mechanisms, but they are claimed that are important. But we still don't know what is the relative importance of the different mechanisms in relation to each other. So if we think that the mechanisms are imprinting some patterns, imprinting some variability in the tree vita rates, we can take one step backward and make this question in a different way. For example, we can think that first, to have an idea, to organize the room, so to speak, we would like to ask what are the sources of variability in vita rates? So this careful assessment of these different sources of variability may give us an expectation of these different mechanisms, that the relative importance of the different mechanisms themselves. So, for example, the main, okay, maybe this is easier. Okay. One of the most obvious source of variability in vita rates that influences vita rates is the difference among species. So if you're in a forest, we can have trees of different species that have different vita rates, for example, growth rates, and it's related to the life history strategies, maybe related to the different traits of the species, and also it gives different demographic niches for those species. Of course, we can have the spatial variation in vita rates, for example, if for differences in soil nutrients or topography, where in some areas of the forest there may be a higher mortality than the other areas, and also the time variability in vita rates, for example, given some drought events and higher mortality, or some climatic events that may happen through time. So in addition to that, we may have the interaction between these main dimensions of variability in vita rates, for example, species-space, species-time, and also space-time interactions. So each of these, we can have, I'm giving here just examples of the different mechanisms that may be introducing variability in the vita rates. For example, the spatial niche, the temporal niche, and also, for example, for space-time gap dynamics. So another source of variability in vita rates that is not a unique, or we cannot attribute a unique group of mechanisms is we call here the residual, because it may introduce the individual variability in vita rates. For example, intraspecific variability. For example, given by ontogeny, where trees of different ages may have different vita rates. But of course, in the residual, we may have this inherent variability in the system, and also because it's empirical data measurement errors. So here we are presenting this first idea of what we call the organizing principles. So principles that may help us to organize the variability in vita rates. So with this, we can give an indication of the ideas of the groups of mechanisms that may be introducing, creating variability in the vita rates. So in this idea, we are proposing this framework. We are working with that, with these organizing principles as these groups of mechanisms that are introducing variability. We are using forest dynamic plots information from them, and using multi-level models and the variance partition is to separate this grouping variability and the total variability of the data. So with that, we have this patterns of relative importance of these sources of these organizing principles. So the aim of this project is to create this framework and then to apply them to a set of large forest plots across the globe. And to guide us, we are asking two main questions. How does this relative importance of organizing principles vary among Vita rates and also among forest globalists, to have a macroecological pattern of this organizing principles, this variation. So we are working with 21 forest plots in the globe. So these forests are representative of very distinct environments and also climates, but I want to stress here that I have plots with huge difference in species richness, from less than 20 to more than 1,000 species, so it's quite different. Just to have an idea of what kind of data I'm dealing here, we have, each forest has an area, and then each tree with more than 1 centimeter in dBH is measured, is tagged, and it's monitored through time. So here we have each dot here is a tree, and the tree belongs to a species. It's in a specific spatial, it's a specific quadrant in the forest, and also we are measuring the Vita rates into this interval between the censuses, which is normally into 5 years. Okay. For the methods, we are using, as I said, multi-level models. So note here that I'm not taking any predictor and a fixed effect, as I saw in the previous, the first presentation. We are using then this random effects, and each random effect represents one of my organizing principles. So it's a very, well, ideally simple model. And then we use the variance partition component, which is simply the proportion of the variability of each of these organizing principles. So to the model, I'm using one model per forest and per Vita rate, growth, mortality, and recruitment. So the first result here is we want to see this pattern of organizing principles and comparing among these Vita rates. So these plots here, they show, I'm using here just the reduced model, because not all forests, unfortunately, not all 21 forests had enough censuses to have any temporal variation. So first I'm showing here for growth, mortality, and recruitment, and each of these organizing principles that we are showing. And in the right side, we have the mean across all forests. So first interesting result is that, of course not, but residual had a huge importance for growth and mortality, a bit less for recruitment. And we have to remind that it may include individual variation, as, for example, ontogeny, which researchers know that it's very important to calculate Vita rates. But of course, it increases other variation there. Okay. We see that species was a very important organizing principle, so a great source of variability among Vita rates. And we have to remember that difference among species are more related to evolved life history strategies, and then it can be related to traits, and then it creates this demographic niches across species. But the good thing also is that we have, yeah. So we had the species-space interaction, also important, and we can trace that back, for example, with spatial niche, where the same species may have a different Vita rates, for example, growth or mortality, in the different areas related to habitat preferences and so on, or also biotic interactions, very local ones. And yeah, for recruitment, space was an important organizing principle, yeah, just for recruitment. So now, talking about the temporal organizing principles, we had only 5 forest plots in the tropics and subtropics with enough information. And I'm highlighting here just the temporal organizing principles, and then we can see that they are very important for mortality and recruitment. And then we have here the space-time interaction that is huge for the recruitment. And then we can trace back also like to think about the gap dynamics when a big fallen tree may increase mortality and then recruitment, and then it's a spatial temporal phenomena. And also this temporal organizing principle varying also a lot for recruitment. So now we want to see a big pattern, a macroecological pattern to organizing principles across the forests. And here we are using species richness to compare forests because we know in our data we have a huge variability in species richness, and then we also know that species richness also correlates with many environmental variables, and also, as we can see here, latitude. The colors are the latitude, absolute latitudes. So the main interesting result here is that globally, the variability among species is less important in species-rich forests, which we thought may be contradictory, but we also investigated that further for some robustness analysis, and we would think that this decrease in the relative importance may be related to a larger variance of other organizing principles, but no, the variance among species decreases in the most rich forests. So this is in accordance with some other results that saw that the most diverse forests have the narrowest demographic niche ranges. So it means that if you go into a rich forest, you will not see so much of this interspecific variability in vita rates because we can think that more forests maybe introduce redundancy in the species, in the demographic rates, and it's more related, of course, with maybe species spec, niche sharing, and these niche ideas and mechanisms. So we can think that maybe with this idea, with this framework, we can imagine if in an average forest, what would be this organizing principles, what would be the variability among them. And of course, we see that the species is globally the largest attributable source of variability in vita rates. I said attributable because we still have a large proportion of the residue that we cannot disentangle it so well. And we see that species organizing principles, so the relative importance of the species, the difference among the species decreases with species-rich forests. The spatial and temporal organizing principles are only important when interacting with other sources. For example, for growth, species-space interaction was very important, and also for mortality and recruitment, the space-time interaction was quite interesting. So, and it also depends on the vita rate. So depending on which vita rates you are looking at, this relative importance are different. So what we have here is that, well, with this simple framework, with this simple conceptual framework of trying to organize in the principles that are introducing variability in vita rates, we can decompose the source of variability, and it can help us to identify these main sources, and it becomes an avenue for future research, trying to test the mechanisms themselves. And so this idea, this framework, this model can serve us as a baseline for expectations and comparisons of this relative importance of the groups of mechanisms that are introducing variability in the vita rates. So yeah, we believe this may be useful to better predict and understand these multiple actors that are influencing tree demography. So with that, thank you, and I'm open for any questions if we have time.
Thank you, Melina. We have time for one question.
Thanks, that's really, really fascinating. And as you were talking, I was sort of thinking about how these individual vital rates contribute to population growth rates. And I was wondering whether you have been able to sort of combine them to estimate population growth and thereby understand the contribution of those vital rates to population growth. And I was wondering if you did that, whether that would affect how you interpret the importance of these different mechanisms. So, you know, space might be very important for recruitment, for example, but if recruitment isn't really driving population dynamics, then it won't be so important at a population level.
Okay, so, well, I have not thought about that before, like to increase, like to upscale this idea of population dynamics. It's a great idea, so maybe we can talk later. I don't know, like it's a nice idea. One idea that we have that we are still developing is like to simulate mechanistically, simulate the forest mechanistically, and then to use this framework to see if we are really looking at the patterns, like the patterns are really representing the mechanism that we are creating in this simulated forest. So this is the next step we are taking, and yeah, maybe we can think more about that, like this results like for population dynamics. Nice, thank you.
Thank you, Melina.